So, welcome everybody. I guess, microphone's working? Can you hear me? Okay, great. It's gonna be hard for me to stay close. So, yeah, well, you can see who I am on this slide, but today I better give a little bit of context on my biography so you can understand what I'm about to say later. I'll tell a couple of anecdotes. If the time doesn't work out, I'll just leave out an anecdote, so you can just ask questions at any time you like, even though this is not one of those chess timer talks. So feel free to interrupt. Don't worry, that the time is not going to be enough. Um, so a long time ago, it feels like a very long time ago, I was a researcher in programming languages, focusing in functional programming. And I think I'm one of the few people who had papers at the ML workshop, the Haskell workshop, and the Scheme workshop. So I'll talk a little bit about the impact of using different functional programming languages in various projects today. Um, Now, in 2003, again, a long time ago, I quit and I became a freelance software developer again for a couple of years. Obviously, coming from functional programming, I thought, uh, it was, this was big in research back in those days, but I thought it would be a great idea to apply functional programming in industry, and I set out to do that. And as I was by myself during that time, um, it was kind of an uphill battle. But since 2010, things got a little better, and I became CTO of a little software company in Filderstadt, Germany. And so I'm going to talk about some of the experience from my time as a freelance software developer, but primarily about some of the recent projects that we've done at that company. So just a couple weeks ago, we rolled out a piece of software for a major automobile services provider that every German who owns a car needs to go to periodically. And they have a lot of workstations, so people take their cars to those workstations. At every workstation, there's a little closet, and that closet used to contain a stationary PC and a printer and some analysis equipment for cars and other pieces of hardware. And for some reason or other, this company transitioned to using mobile tablets. Instead of having a stationary PC at every workstation, they would give every employee a tablet. And once they sort of done the planning of that, they realized that it's not going to be good enough to just give everybody their tablet and everybody would be happy, but really you need to reconfigure this tablet depending on where it is. So, if some employee takes their tablet from one workstation to another, or from one site to another, or outside of a site to a customer site, um, and they press print or whatever, they don't want that printout to come out at the printer where they were. They want the printout to come out at the place where they are. And the same goes for various other pieces of hardware. Some of it is USB hardware, Bluetooth hardware. So we were commissioned to write software that would reconfigure the tablet um, according to where it was, and would try to find out where it was, and then make configuration adjustments. Now the problem with that is that, a lot of the time, one of those tablets would be connected to Wi-Fi, but a lot of the time it wouldn't. And still, you wanted to be able to do that reconfiguration. So, one issue that came up immediately is how we were going to communicate to a tablet information about the configuration of where it is. And we ended up saying, well, we obviously can't go with the classic, client-server model here. We really need to communicate configuration information between the tablets. And the easiest way to do that was to do it via pairwise synchronization. So whenever two tablets would meet, they would be able to exchange configuration information and just send the information that the other tablet doesn't have to that other tablet. And so, for example, the way it works now is that if a tablet would enter a site, it would log into the Wi-Fi there, and then it would immediately know to send a broadcast message to everyone else at that site and saying, well, I'm new here. I need configuration information about this site. And then hopefully some other tablet would say, well, I'm here. I know what's going on. And we too should hook up and synchronize the configuration information. And now, as I said, this network, it has limited capacity. It's transient, so you really need to get things done quickly. Over time, we've been surprised by how much configuration information these people accrete. You really only want to exchange the configuration blocks that the other tablet doesn't have yet, right? You don't want to just send over the entire database and then have everybody figure out the union of their blocks and the other blocks. And so, you want to figure out that a lot of the blocks are going to be common, asymptotically at least. And you really just want to exchange. You want to then figure out what the blocks are that you want to exchange, and then you just want to send those across the wire. And, this is we've seen people fail at this in this environment, but so we knew we needed to maybe apply a little bit of computer science to this problem. And in fact, there's a great deal of wonderful literature on synchronization problems that gives you, sets up criteria that you can apply to your problem, and then lets you choose an appropriate method to actually do it. And we ended up using a lot of those approaches are actually based on something called a Merkle tree. And the way that works is, well, you have all your data blocks here at the bottom. And what you do is each data block gets computed a hash code, and you then use some of the bits of that hash code to compute a path in a tree, right? So, and as you go up in the tree, and you have internal nodes that that stand for a subtree, and in that subtree are a bunch of blocks. What you do is you compute a composite hash of all the blocks in that subtree, and you do that all the way up in the tree. And the great thing about Merkle trees is, well, the hash code at the top, right, represents all the blocks that you have on your machine. And if you synchronize, you can start by just talking about that hash code at the top. And if it's identical on both machines, you're already done. You know that the other machine has everything that you have, and vice versa. And if it's not the case, you can go down the tree, and now you have two hash codes, and maybe one of them is going to be the same, in which case you can eliminate that subtree. And the other one is not the same, in which case you go further down the tree. So you go down, you kind of you widen at each step as your tree gets wider, and you also narrow as you eliminate subtrees that the other side already has. So at each step, it's kind of like Japanese people exchanging business cards. You send a message over, and synchronously as you get to the bottom, and then as the last step, you've narrowed things down to a specific set of data blocks that you need to then send to the other side, and then you're synchronized. And you can go about your business and do configuration. And that's worked exceedingly well. Now, in code, this needed to run on Windows, and the language of choice on Windows is F# these days. So here's some of the actual production code, which was a very naive approach to implementing this, but which worked out fine. So a Merkle tree is just, so I said some of the bits of the hash code get used as the path in the tree. That's what we call a signature. And of course, as you identify a subtree in the Merkle tree, you have a prefix of that signature, of all of those signatures of all the blocks that are down that subtree. So a Merkle tree just consists of a signature prefix that identifies the subtree, and a list of hashes of all the blocks in that subtree, and the signatures of all of those blocks. And then, a signature is just a list of numbers, and a signature prefix is also just a list of numbers. So it's very, very simple. Now, of course, you don't want to send the entire subtree over. You just want to send what we call a fingerprint, which is just the signature prefix, which identifies the subtree, and the hash code, the composite hash code of all the blocks in that subtree. And then you exchange messages that look like this. Either on an internal node, you say, well, I have these fingerprints to tell you about. Or you say, at the very bottom, you say, well, I now know what blocks you don't have that I have, so I'm going to communicate them to you. And this being functional programming, you can write this in a purely functional fashion. In fact, you can do it without even explicitly constructing the tree, which is what we did as a data structure. And you get at the core, you get a function like this, which does one round of this synchronization, which says, well, here's all the hashes that are in the system. Here's a set of Merkle trees that I believe the other side doesn't have yet at a certain level. And there's a message I'm getting from the other side, right? And so I have something. I suspect the other side doesn't have something. The message is going to tell me more about it. And as a result, I either produce another message to send to the other side and a new Merkle tree set one level down, or I'm already at the bottom, which is a list of hashes to send to the other side, right? And looking at the signature and knowing the basics of this, you already know what it's going to do, and you have enough knowledge to test it. And so, one of the great things about functional programming is you don't have to worry much about, setup and tear down methods and what you need if you're writing unit tests in imperative languages. So you can think you can think up two blocks, two sets of blocks, and you can just run the algorithm, and then you can say, well, afterwards, every side should have the same set of blocks. So if you union the blocks that you have with the blocks that you get, and also you can test that you don't get any blocks redundantly from the other side. And that's what this code does. And even if you don't understand every detail, you can see sort of it works via set operations. So it's not a big deal. And now the next great, so now you write unit tests, which are individual examples, but David Nolan already talked to you about this, is individual examples are often not enough. And as you're manipulating bits and hash codes, you can have subtle bugs. So it's better to write these things down as general properties rather than individual examples. And this says, well, for any sets of blocks, BS1 and BS2, the properties from the previous slide should hold, right? And then you can use quick check, which you now know about if you were at the keynote, to generate test cases automatically. And that flushed out one or two subtle bugs in the algorithm. Now, first of all, I'm not very big on algorithms, and we figured everything else in the system was going to be pretty simple, right? We just need to reconfigure the printer or the Bluetooth or whatever it was. So we figured that, as we went towards deployment, we would have, the area where we expected the most problems were that complicated algorithm and the pragmatics of running that algorithm in sort of a hostile environment. And much to our pleasure, using those, quick check generated tests, this system has now been in deployment. And, it's exhibited 0 bugs, right? It's now running on about 1,500 machines. And these customers, I haven't told you about this, but really, if this piece of software doesn't work, they lose money, like right there. If it doesn't work for 5 minutes. So these are customers that call us, if there's a problem, and they haven't called about any problems with this. But before we did deployment, and of course we did a lot of testing before deployment, we had a lot of problems, right? We had auto configuring printers on a Windows system is a nightmare. Mounting drives there's 3 different APIs, and just generally tracking a changing environment, or just getting the GUI in sync with the internal state of the system. All of those caused problems exceeding those that we had with the synchronization. And an embarrassing amount, a lot of these things, like, the customer would call and say it didn't work, and then we changed the software, and embarrassingly often the answer to something not working is we would just wait for 5 seconds and try again. And then, a lot of those problems go away after 5 seconds for some reason. But what they all have in common is they deal with mutable state, right? And in this case, a lot of that mutable state was unavoidable, except maybe for the GUI stuff. But still, it was a good lesson to repeat for us, is really that we should keep the use of mutable state to a minimum in our software, right? So, and we've learned that lesson many, many times and through many projects. Questions so far? Okay. So, because I'll switch to a different project now, which dates back to 2003, when I was still a freelance software developer, and one of my first clients was a very large, at the time, very large German bank. They're no longer that large, and they're no longer German, but and they called me up, and to my surprise, they said, well, they were doing financial derivatives, and they said, we're doing financial derivatives with a system called Scheme 48. You need to do a lot of computation, and as you have complex financial derivatives, essentially the only way to evaluate them, at least at the time, was to do simulation. And so they had a large cluster of machines, and they were running distributed Monte Carlo integration, which was being coordinated by a bunch of Scheme 48 code. And just a few weeks ago, I learned that it's still there, even though I haven't worked for the bank in more than 10 years. Now, that surprised me. I mean, it didn't surprise me that they called me, because at the time I was the maintainer of Scheme 48. But Scheme 48 was a research system with, experimental in many ways. And somehow they decided that that was the best thing for them. So that's just a side note, though, because when I eventually started working for the bank, the problems were much more profane. What they wanted to do is they wanted to deal with market data. And you all know that a lot of market data gets generated by trading, so you have spot prices for a lot of things that get traded directly on the market. But as you get to complex derivatives, a lot of that market data is derived from that sort of primitive market data. So, in derivatives, or generally in finance, you deal a lot with volatilities. Volatility is a measure of how much something changes. So these are old slides. Um, um, and as you deal with derivatives, you often don't deal with individual entities that are being directly traded, but you deal with groups of them, so-called baskets, or even your usual whatever Dow Jones Industrial Index is a kind of basket, which is sort of a weighted sum of the members of that basket. So, but the thing is that a lot of those things, a lot of those baskets are usually not traded directly. So, but you want to treat them as one entity, so you have to make up market data for those baskets. And you can imagine that those baskets, you kind of have a tree where there's primitive market data at the bottom, things computed from that in the interior nodes, and then there's ultimately derived quantities that you use in your software at the top, right? And now, the traders, the people with the suspenders that you see on TV, they don't just want to know about their portfolio under current market conditions. They want to know what happens to my portfolio if something changes in the market. So if some individual call option goes up 1%, but that's often not very interesting because that's going to have a minuscule impact. But sometimes you want to know what happens when you shift an entire volatility, what's called a volatility surface, which is a bunch of those things grouped together, or you want to know what happens, if the entire Dow Jones goes up or down, what's going to happen to my portfolio, or even the entire market, everything goes up or down, right? And for this stuff, they were using a bunch of object-oriented C++ code, and the way that worked was to use actual code. The way that worked is you would have a class called market data. There would be an instance hooked up to various real-time feeds, and you could ask it, what's the spot price of that thing? And that thing was identified by a number called a sycovam. Don't ask me why these strange types, but this is real production code I didn't write. So, so you have market data that corresponds to the actual real world, right? And the traders wanted to know market data that is just like that, but a little different, right? And in object-oriented programming, what you do is when you want something that's the same as something you already have, well, you write a subclass and you override a bunch of methods, right? Now, the traders, of course, they didn't want to compile their C++ program every time they wanted to compute a scenario, so we needed some dynamic solution. And as an object-oriented programmer, you open a patterns manual, right? And right there it has a decorator pattern, which says, well, it's a flexible alternative to subclassing for extending functionality, and that works at runtime. I don't want to spend too much time on the details of that, but a decorator means that you subclass it once, and you put a delegate in there, and that decorator will call the delegate for all methods except one, typically. So, so for example, you would do it like this. You would say, well, how about this? The entire market shifts, so I'm just going to override the method for get spot. I'm going to call get spot on the delegate, which is that F market data thing there, and I'm going to multiply that by a certain factor, right? And now, unfortunately, this doesn't work quite as you expect, because for baskets, or for things that are composite entities, right, we know that the spot of that basket gets computed from the spot of the members of that basket, so there's a recursive call there. And the way object-oriented dispatch works is that recursive call goes to the spot shifting method again, and so you get double and triple shifts depending on how deep your tree is. And so, I have to admit, at the time, I thought, object-oriented programming has something useful to say to this, right? This is like one thing in the system they did right. They did a lot of things even wronger than this, but until we found out that, and there's an entire talk about what they did to remedy that problem. But, ultimately, I really needed to go back to what I knew as a functional programmer, is that I should really model transformations on the market data as functions and combine them by using function composition. Right? So you have primitive transformations, tau 1, tau 10, tau n, and you can just compose them. You again have another transformation. You can compose them with others, so you get kind of a compositional combinator model for this. And that's a lesson that I temporarily forgotten. I had a lot of things on my mind transitioning from academia to industry at the time. That's my excuse. But over time, we found these compositional combinator models in many, many, many applications, and it's always worthwhile looking for them. So that's one of the lessons from the talk. apart from the purity from the first example. So even in domains which seem very flat and boring, uh, you often find compositional structure, and it's worthwhile looking at for it. And you often, when you tell your customer about this, we often found that this conveyed some kind of insight in their domain that they didn't know themselves, because just it arose from a systematic kind of modeling. So, this is just a partial list. That list gets longer and longer. In particular, one domain where we've been called upon to apply this was in the domain of semiconductor manufacturing. Um, Switch gears a little bit. And I don't know if you know this, but making a semiconductor is a very complex process. Making a modern microprocessor takes something like 6 weeks, and there's like 1,000 steps involved. And when I started out, I thought, there's a big old machine. You put in a bunch of silicon, you pull a lever, and it doesn't work like that, right? Unfortunately, so there's multiple layers involved, and the machines are so expensive that you can't just make an assembly line, right? There's some machines you just have one, right? And so all your wafers have to go through them. They have to go through them multiple times. Your average fab these days makes many different kinds of wafers. So this big machine that this semiconductor fab constitutes is very, very expensive to purchase and run. So you really want it to run as efficiently as possible. And there's a lot of things that complicate the scheduling problem there. Nobody knows like a closed form solution to this. And so I figured for some of the problems that I was facing, I wanted to know if a certain scheduling decision was right or not, or if it was going to get us benefit down the road or not. And the only way I could think of how to do this was to do simulation. And I fell into the same trap that I'd fallen into 10 years ago, 10 years before that, which was I thought, what was this thing that was originally developed for simulation? It was this object-oriented programming, right? And so I wrote code that looked like this, right? There would be a tool in the fab, and I would install it by saying, well, here's an identifier that I can use to refer back to it, and here's a description of what that tool does. And you can see this is an esoteric language that we were using at the time called star. And it returns void, doesn't return anything because it installs information about that tool in the global table. And I learned this, so second time this shows up today. I learned this from one of the great books in computer science, Structure and Interpretation of Computer Programs, which tells you this is how you do simulated worlds, is you have global tables where you install things. And, it didn't work out very well because, in the fab, we wanted to do simulation as the system was running. So there was no option of modifying the current state of the system, even if it was just for a simulation, because that state was needed in the actual running system. And then, of course, we sometimes also wanted to examine multiple trajectories or even run that recursively. As you run the fab and you simulate the fab, you also need to simulate the scheduling, right? And so we really needed simulation to be re-entrant. And then I got to thinking about it, and then I realized, well, I've known this all along. Simulation, the real world is not object-oriented, right? And our perception of the real world is not object-oriented. It really works better, much better, if you think of it in terms of consistent snapshots. And so that's what we ended up doing is we took a big snapshot in a pure data structure using a lot of the techniques that you saw David Nolan's cite from Chris Okasaki's book. And then have the system progress by computing new snapshots, which share a lot of memory with the old ones, but which are conceptually independent. And that allowed us to do a lot of things instantly, which had been very hard previously. In particular, we could run a lot of simulations in parallel. We could examine many different paths without having to worry about affecting the state of one of the other paths in the system. So that was a great point for purity at that time. And then as we kept on developing the system, we were thinking about the actual scheduling algorithms. And one of the problems in the fab, one additional problem in the fab is that things break down all the time. So some of the scheduling systems that you can buy on the market, they compute a big old plan, right? And they optimize, they use, fancy optimization algorithms to optimize that plan. Unfortunately, that plan is going to fail after about 5 minutes in a typical fab because some piece of equipment which operates on the level of quantum physics breaks down or needs to have maintenance or goes out of spec or something like that. And being from Germany, I need to make a soccer analogy. Is really, so the thing that we really had to deal with is we needed to anticipate that things might go wrong. in the system as part of its normal operation. And so if there's a penalty kick in soccer, I don't know if you know this, and if you're the goalkeeper, then you need to make a decision where you're going to jump before the ball leaves the foot of the player, right? Just because of the way the physics works out. And so you need to hope that the ball goes in the corner. Oh, you know who this is, right? Yeah. So this is Hope Solo, the goalkeeper of the American national team. So I was thinking a lot about this notion of hope in the context of the fab, and I was thinking, well, you give the fab a concrete instruction. You're not going to get direct feedback that it failed, but you hope that it succeeds, and maybe later you'll find out that it hasn't happened. And the code got very complicated that I was writing at the time, because I was trying to model many different concrete situations in the semiconductor fab. And I was getting very frustrated, and that led me to thinking, maybe I should think about hope in more general terms, right? What is hope? So there's like pure hope, where you hope that something happens and you have no way to influence whether it's going to happen or not, right? Oftentimes you can, that was essentially the situation in the fab. We would give the fab an instruction, and we would hope that it gets executed. Sometimes your hope doesn't materialize, so later you reiterate your instruction, installing a printer driver on Windows or something. So you just do it again, right? You issue the same instruction again, then you hope that it's going to work out. And ultimately, some things are just not meant to be, and you need to make a decision that something, your hope is never going to materialize, and you need to act accordingly. As I was thinking about this, I had a tour in an actual semiconductor fab, where you could walk around and everything was glass, and the tour guide would point out and saying, oh, this lot, this was sitting there last year, because some production step hadn't materialized and people just forgot about it. So, you really want to manage this kind of thing. And so I was drawing this little diagram. I said, well, hope it may be shattered, right? It may be fulfilled, in which case it produces some kind of value. Underneath, you have the fab operating, and sometimes hope transforms into another hope. For example, if you hope that something happens, and then after that happens, something else happens, or you say, well, you can think about combining hope. You can say, well, I have this hope, but I really want it to happen by that time. And so you get a combinator model for this thing. And if you look at this closely, you can see that it's a monad. So, if there's a catchy slogan you can print on a t-shirt, it's hope is a monad, right? That came out of that. So we went on to find other abstractions, which are high-level esoteric abstractions that we do in functional programming that were directly applicable to this domain. So it's always worthwhile to keep those in mind and keep those in your arsenal. So that was another success story for not just functional programming, but for using fancy compositional abstractions. I want to put a little sobering note on this with another project I was working on, which also was a success, but qualified success in some ways. So this is a project I inherited from somebody else, and you can see it's a bunch of Haskell code. And it was for, essentially it was for implementing a very large state machine for controlling an embedded control system. Unfortunately, I can't tell you what it is, at least not here on video. But you can maybe ask me later. The way these systems are specified is you specify a state machine, and the way it operates is also by a state machine. And so my predecessor implemented a DSL for writing state machines in Haskell. You would see monadic syntax, and you can do, if you know about state machines, this is actually understandable code, especially if you know about the application domain. And then he was able to use abstraction in Haskell to really build up the state machines in a systematic fashion. So that was great. And not just that, he was able to implement temporal logic system for examining the traces of those programs to do automated testing. And so this was, again, an application of another fancy concept, even if it's old, that was very successful. And that's another piece of software that I don't think has exhibited a single bug since then, and I didn't do it. The identifiers are so long because they're in German, right? So you can see you kind of going, well, what is this? They're German words. You're not expected to understand them. Huh? Yeah, whatever. Something like that, yeah. Now, one fancy trick in the software system was that the DSL was expressed as operations in a bunch of type classes, and there's no abstract. Usually, you would implement a system like that. You would like have an abstract syntax, and from that generate. So I need to backtrack even more. The Haskell code doesn't run on the embedded system, right? The embedded system runs C code, and the way this worked is you would run the Haskell code, and the Haskell code, the only thing the running program would do is would emit C code that you could then deploy on the embedded system, and that then would get automatically tested by this. So that was great, and the system was able to get by without abstract syntax, for example, just through clever uses of type classes and monads. So that was wonderful. And system was deployed, and then my predecessor quit the company he was working for, not my company. Um, and 1 or 2 years later, the customer sort of resurfaced and said, "Well, we don't really want the C code. We really want code written in a language called SCADE, which is very widely used in those circles, which has, for example, a graphical notation for specifying state machines, and which is, there's a lot of research papers on this, and there's a lot of ecosystem infrastructure, and more importantly, this is certified for use in sort of mission critical domains. And so they wanted SCADE code, not C code, and then they would generate the C code from the SCADE code. And now, but the original code, not only could it only, I mean, the only thing it could do was generate that C code. Um, it didn't have abstract syntax or anything, so it was not really that easy to just plug in a different backend. And when somebody went in and just wanted to resurrect that code and compile it with the current GHC emitted a bunch of very obscure and long type error messages. And there were still a bunch of Haskell people at that company, and they all gave up on just getting that code to compile. And the fundamental reason why that code wasn't compiling was that every single file started like this, right? And all those features then got used within those files. In some aspect of the inference of the resolution algorithm in GHC had changed, and the code was sensitive to that. And it took a whole lot of tinkering just to get the code back to compiling, and then a lot of work to sort of get the code in a shape where I could plug in a different backend. The actual backend was trivial after I'd done that, right? And I'm sure it must have gotten a lot of tinkering to get the code working, in the first place. So there's this problem, if you have these fancy type systems available to you, with existentials and polymorphic variants and GADTs and whatnot, is that you want to use them to model your domain as precisely as possible, right? You want to take good advantage of the tools that you have at hand. But just the other day, I was writing a bunch of Scala code, and I was just trying to make like a heterogeneous map with, where the type would determine the key of where the key would determine the type of the value. Implementing that was trivial, but getting the type checker to accept my proofs that it's actually type correct, took me another half day. And I see people doing that a lot. So, and here's sort of the conundrum in this field, is that we're doing functional programming to program in a more systematic manner and sort of an engineering fashion. But when it gets to the type level, which should push us towards more systematic programming, the practice of it often is a lot of tinkering that looks like this. So, our next big project that we did in the semiconductor fab domain space, that diagram doesn't mean anything really to you anyway. We implemented an enclosure, and it has a lot of purity, and it has a monad staying right at the center of it. But in particular, that monad I know it takes some very fancy type gymnastics to get type correct, and it's no big deal in Clojure at all. So I like to take good advantage of fancy type systems, but I would like to do it without a lot of tinkering. And right now, the state of the art isn't there yet. So let me summarize. Functional programming is wonderful, and it took me 10 years at least to realize that I would do a year of functional programming, and that for some reason or other I would have to do a little bit of object-oriented programming, and it's always worse than I remembered. You get the past. You think this object. A lot of people are doing object. It can't be that bad, right? But it is, and it's worse. Or conversely, functional programming is that much better and that much more pleasant to do. So the main aspect for us that's relevant in our day-to-day work is really to do purely functional programming. A lot of functional programming languages give you imperative features. I mean, all of them do. and you do well to avoid them and to model things in a pure fashion. Especially because purity gives you a way to do programming systematically. I haven't talked a lot about that. Matthias Fellheisen's here, Matthew Flatt is here. Those are people who pioneered not just programming systematically, but teaching people how to program systematically. And so this is all eminently teachable. Um, Type-based programming, also haven't talked a lot about that, but systematic programming is a lot of, when you do that, you should really do it thinking about the types of the things in your system, right? And I think the closure people as a whole have yet to learn that. But I'm a lot more ambiguous on the benefits of static typing, at least given the current state of the art. And if you're a programming languages researcher in type systems, don't just think about the fancy logic that you might apply, but also think about the requirements that arise from practical programming, which are not just about, fancy types, but which are about modeling things in the real world and doing that systematically. That's all I have to say. Questions? Yeah.
Question. When you are confidence, so that means that you work for our company, and that you have a problem to implement these ideas with other people who said, no, it should be done object orientedly. And was that the reason why you found your own company so you can do it your way?
No, no. So I didn't found that company. That company existed and hired me as a CTO, so I should say that. But good point. Thank you. So the question was whether I founded a company because people before that told me no, object-oriented programming is better at functional programming for modeling things. And I've never heard anybody say that to me. Um, uh, I think people use object-oriented programming in my domain in Germany, where people are very conservative about new technologies. It's just people like to use technologies that everybody else is using in many ways. So that's the argument that I hear most commonly. There's no, especially if you model things, there's no. I probably conveyed that impression wrongly, right? The fundamentals of object-oriented programming are great for modeling things, right? The problems come with the introduction of mutable state into object-oriented programming. And arguably, it was one of the original goals of object-oriented programming to get rid of mutable state. So there's that early history of Smalltalk paper by Alan Kay, which says that very explicitly, but they never got around to doing it. So, one way to view it is sort of that functional programming is now coming to becoming the realization of that original dream. So the data modeling techniques, and I think, what was great about object-oriented programming is that you do conceptual modeling. We can talk about that all day, but having a good, a close correspondence between the objects of your program and your problem domain, that's great. And that's eminently applicable in functional programming as well. Does that answer your question at all? I don't know. Okay. Yeah. Any other question? Yeah. Oh yeah, lots. Yeah, we're still a small company, so I mean, a lot of projects we just don't do because of that. We've been foolish on some projects. I remember, we were foolish to say, well, we can do this two ways, right? We can do it using functional programming, or we can do it object-oriented programming. In which case, it costs you plus 50%. And we've had customers who didn't even blink and said, object-oriented, right there, right? And we were like, oh, and that's how we know how awful it is, right? Is right? It's when these projects come along. We always thought we were going to give them an easy choice, and sure enough, we gave them an easy choice. It just didn't come out the way that we wanted it to. So, um, yeah, but it's getting to be less and less, right? People know these days. I mean, everybody knows what functional programming is. Most everybody knows is that it would be better if they were using it, right? And I know 10 years ago we were like, people would say, Manuel's not here, but he used to say, don't say the M word. You can't say monad in front of like ordinary programmers because they get scared. And that is certainly no longer the case. Now it's a cool world, right? It's a, if you know what a monad is, you get a certain status even among Java programmers. And I've got a little sort of unscientifically but hard evidence, collected but hard evidence on that. So there's progress. So, one more, and then I guess we'll break. Huh?
If dependent type systems help at all with semiconductor?
I had that in my note. Yeah. Oh, the question was. I'm sorry. I need to repeat all the questions. So, the question is, will dependent types help? And my notes somewhere mention that I hope that dependent types will help with this, right? And I haven't seen it happen yet, right? Dependent types were introduced in Haskell. I asked a couple months ago. I asked Stephanie Wyrick, which feature of Haskell can you now take out, right? I mean, ideally, it would, the dependent types would subsume some of the other features in the Haskell type system. She said none. So I'm not deep enough in that to really make a judgment call. But I really hope that, and I think that's the best avenue that I see right now, is that dependent types will just make things more uniform, um, and help us getting maybe less fancy, but more programmable and more uniform and type systems that allow us to get by with less tinkering. Okay, I guess we'll break then. Thank you very much.